Welcome back to this channel, and this is the last part of the APCO measurements using FieldFox. So we're going to deep dive into another alternative of measuring the APCO signal. So one of the test methods that we normally use for measuring a digital signal such as APCO25 is using a test parameter called EVM, error vector measurements. So if you want to go into detail on that, you can actually just look through the YouTube links, not just my channel. There are some other channels that can explain to you much better. So essentially, it's just to make sure that constellation of IQ data is at the place where it should be. Any deviations from that constellation point will contribute to the quality of your data transfer. I'll go straight into how to set up the VSA software to do APCO25 EVM measurements. VSA software only runs on Windows machine, and this is something that you have to be aware of. Assuming that we are out in the field right now with a Windows 10 tablet and running on a VSA software that's communicating to FieldFox as a receiver, and this is going to be the setup when you want to do EVM measurements on APCO25. So as you can see right now, there's some signal activities on the FieldFox at the same frequency that we did in the previous video. So this is done and dusted, so we have everything there. So we go straight to VSA software, and because I just disconnected the hardware, so let's go to utilities, hardware, analyzer, hardware again, and just click play. So once you say acquiring 9918B, and this is the screen that you're going to see here. From there on, you can't actually access to any of the buttons on the FieldFox because all the resources have been pulled to work with this VSA software. Alright, so let's go through step by step. This is the first default screen that you're going to see on a VSA software. So because this is a digital signal, so you just go to measurement type, general purpose, digital D mode. So in digital D mode, we normally have 4 types of measurements here. So let's change that view. So go to trace layout, 2x2, and this is how it looks like. And this is where you can start doing things like changing the frequency, measurement setup frequency, because we know that it's 420.475 megahertz. And we don't see a lot of activities here right now. This is alright, and I'm going to change the span to lower to about 50 kilohertz. So currently you see that there's some activities there, but it's wrong because we don't have enough sample to do the measurements. So the other things that I want to do is go straight to digital demo property, and I can go to preset the standard. So APCO is here. So this is the base station. There's no complex modulations involved there. So I just go to this APCO25, and symbol rate is supposed to be about, I think, 6. Then the next thing I want to do is just optimize here, auto range. I can't change the preamp and the attenuations manually, and this is what we are seeing here right now, 40 kilohertz, which is about there. And I'm going to optimize here. Okay, it's not really measuring the right signal. As you can see, it's all over the place right now. So what I'm going to do is I'm going to preset it. I might have changed the span too early, and so we can always go back to preset, setup. So again, we go through the setup again, vector, general purpose, digital D mode. Then let's go straight here, others, APCO25. So it says 4 kilohertz. Okay, just assume that that's correct. And then we change the view 2x2, and then we're going to change the frequency. So we can either go through measurement setup frequency, or we go through here. Just click on this, double click 420.475 Mac, and then we optimize or auto range. So let's just wait for some signal activities at the center frequency here, and we should see some measurements over here. So you might be able to see over here the magnitude error is about 57% RMS, and FSK error is about 34%. So we just wait for some signal happening here, and yeah, it dropped down to 2% RMS. So you can see that the signal is jumping up and down, and the line actually overlapped the red dot. So what you can do is to remove that line. Let's go to trace A, which is the measurement here. Let's change the format. So currently, if you want to see the constellations, you will have to choose the measurement time. So under measurement time, there are some other things that you can change to. So measurement time, and then we want to change the format. How it presents itself is under format. So INQ will involve the line where the points move from one to another. Without the line, it's called constellation, just focusing on the INQ. For this case, it's 4 FSK. So that's because there are 4 points here. So you can zoom in here. Can I zoom in here? Yeah, I can try here. So if I zoom in here. So let's look at just 2 points for now. You see that when there's a signal here, the INQ information should be row under the points of interest. Right, and let's go back there. Auto scale it again so that we can see that. So let's see, scale X a bit bigger. Okay, let's just wait for another round. One thing I believe Kisa is working on is to include the GPS informations into this type of measurements, so that when you do the measurements, you know that where the location that you have captured this data. Right, so the next thing I want to show you is that you can actually record this signal, and then you can replay it at the comfort of your office. So let's zoom this out again. Let's go to ranges, zoom this out. Oops, doesn't show anything. Okay, so for recording, I would suggest to do this setup first. Let's go to input, recording. This is where you define parameter of your recording. You want it to be in record format, or you want it to be in seconds, frames. So you can actually do it this way. Like I want to do a time base, so 5 seconds recording, or 5 records, or 5 segments, 5 points. So it depends on what you really want. So let's do a 5 seconds recording. So make sure that the unit is correct. And once you've done that, click that, and then we can wait for the signal to appear, and then we click on this button, record. You just pass all the processing power just to measure and record that signal. And you'll notice that it changed from the record to the instruments icon. So you can see that if I click that, this is instruments. And if I click that, it will be the recorded signal. So you can do post-processing after this. As you can see, we capture at the right time, and it ranges between 1 to 2% of RMS FSK error. So what if you want to pause that signal at a certain point? So let's go to Windows and play it. So this is where you pop up. If you can see here, there's a bar where you can just scroll around, move about, and this is where you can actually do the measurements, post-processing. And if you're really interested to set the start and stop range, let's say you just want to look at here, when you do the recording, the signal is still up and down, and only this portion has the signal up. So you can actually group it, and then you can just replay just this portion without going through the other side of the signal. Alright, this is as simple as that. And so one thing to remember is that all this recording is temporarily stored in the RAM locations, and if you shut down this software, that information will just disappear. So always remember, if you want it for permanent storage, you have to go to File, Save, and save recording. And with that, you can save it as a CSV file, SDF file, or .mat file. So each format has its own pro and cons. If I want to recall this signal again from this VSA software, I will save it as a SDF file. But if you want to use the same recording for MATLAB post-processing, you can save it as .mat. And if you want to do CSV format, it's up to you. Alright, that's it. Thanks for watching.